Moving ahead with our discussion on force control of serial chain robots, in this lecture, I'll cover two more fundamental force control approaches, that is hybrid force control and stiffness force control. So let us begin with a quick recap on the external force control loop and admittance control approaches that I discussed in my last lecture. So external force control loop, as you see, it looked like this. Okay, so it has limitation of positioning robot. The robot, the kind of robot it used was purely positioning in nature, and it wound up its force control loop from an external force sensor that made it inherently slower in response, and whole of the robot was still a position controlled robot, and it had a force sensor at the wrist. So any senses of the forces it could sense only after the wrist and not before the wrist. So the collusion with the links remains undetected. So this was one of the biggest drawbacks of having such robot for force control. Okay, and in admittance control, which was an explicit or a direct force controller, you saw this also had a direct input of forces, that is wrench over here, and it could also take up the trajectory input from here, that is the position set of positions updates can be sent from here, and this also has potential instability limitations, and it was difficult to achieve precise speed control from here. Okay, it was also slower in response because this also was dependent on external force control loop, a kind of external force control loop, because it has a force sensor that gave you a feedback from here. It is very much parameter sensitive also, and it is not suitable for unpredicted environment. So anywhere where you need pure force control to a greater precision, you can use admittance control, but definitely not for achieving precise in speed control. So these two were earlier force control approaches which was in use. So later on, a hybrid force control approach was proposed by Raybad and Craig in 1981. They used a modified JPL Silman Stanford arm with a Maltese cross wrist force sensing. Okay, so it had both the inputs. You see, it can take up the position trajectory from here, and it can also take up the force trajectory from here, and it has two sensors. First one could sense the wrench from here, wrench or the forces, combination of forces and moments. So that is the feedback. So you, because this again used force sensing at the wrist, so with wrist may be oriented anywhere with respect to the base. So that coordinate transformation needs to be done in order to express both the commanded and the actual forces on the same frame. So you need to have a coordinate transformation here. So this is the feedback and this is the desired wrench. Okay, so taking the difference will give you the difference in wrench delta W. Okay, again from here if you see, you have a desired position trajectory input, and this is the actual position. Taking the difference will give you the delta Q. Okay, now what is S and I minus S? S is essentially a compliance selection matrix. Okay, so I minus S generates the complement of compliance selection matrix, which is essentially a diagonal matrix. So whatever it look like this, it looks like this. So anywhere where you want position to be controlled should be set as 1. So if I set 1 here, 0 and 0 here, remaining elements are always 0. It is a diagonal matrix. Okay, so if this is set to 1, okay, any of the element along x is set to 1, so it calculates the difference only along x. Okay, so that when multiplied with Jacobian inverse, it gives you a equivalent theta dot. Okay, so Q J inverse should give you theta dot. Okay, that goes to the position control law and generates a torque here that goes to the joint. So this is the torque which is generated corresponding to the positional error, and similarly I minus S will give you a matrix which looks like this again. So if it is 1, so this becomes 0, this becomes 1, and this becomes 1. So in this case the difference in wrench will be calculated along only Fy and Fz direction. Okay. So that goes here, that is multiplied with Jacobian transpose, give you the torque equivalence. Okay. So that is what, so this is the reference torque that goes through the force control law and generates the torque corresponding to the wrench error. So you can feed this controller simultaneously with the position desired, that is the desired position trajectory, and also the desired force. Okay, and it separates the force and the position subspaces using the compliance selection matrix. Okay, so this combined together, this tau due to the positional error, tau due to the force error, combined together goes and generates the combined torque that goes to the robot. So this finally gives you the Q and W. W is sensed using the force sensor, Q is calculated using forward kinematics. So this is how the combined loop operates. So how is this compliant selection matrix operates? That is decided by the end effector interaction conditions. Okay, let us discuss little more in detail here. Let us consider one example when you want to insert a pellet inside a hole. In this case, as the coordinate directions are shown, so along z direction you need to move, but you cannot move along x and y direction. So if this is x, this is y, the pellet cannot move while inserting along x and y. So you can only send position trajectory along vertical z direction, whereas you can continuously send the forces along x and y direction. So if at all you have to use hybrid force controller for this, so the compliant selection matrix will be like this. So you have z as 1 and these two are 0. So the position difference, the error in position, that position desired and position actual, okay, it creates the delta P that gets multiplied with the compliant selection matrix. The only difference that will be calculated will be along z direction. So corresponding to that, it will create the torque due to the position error along z. So it makes the robot move only along vertical z direction. So position goes along vertical z direction. Now once again, so now if at all you want to write on a board, okay, so in that case you can move along x direction, you can move along y direction, okay, but you cannot move along vertical z direction. So you cannot set position trajectory here. Okay, you can only adjust the forces which is upon contact, which it can maintain along the vertical z direction, that is normal to the surface upon contact, whereas you can write on the board. So you can move your pencil on x y plane, that is along x and y you can set the trajectory. So in this case the compliant selection matrix will be x and y, z will be equal to 0, remaining elements are always 0. So this is my compliant selection matrix. So delta P, that is the positional error, gets multiplied with S, and delta F, so delta F gets multiplied with I minus S, that is force error or the wrench error gets multiplied with this, and you are remained with only the forces which is along Z. I minus S will make a matrix like this. I minus S will look like 0, 0 and 1. So only the difference along vertical Z direction will be calculated. Okay, so you can move along this and you can apply forces along vertical z direction. So this is how it operates. Okay. So now the limitations of this are stiff and position controlled subspaces. Now this also has a force sensor which is fitted at its end, okay, with which it is giving you the feedback of forces. Okay. So again there is an external force control loop, a kind of external force control loop. So again there is some latency, again there is some delay in that control loop. Okay. So it becomes little stiff in position controlled spaces. Okay. And it is difficult to obtain accurate environmental modeling. So you don't know whether it is accurately aligned, the whole direction is accurately aligned along the vertical z direction of the robot, or if the plane is accurately placed so that it matches with the xy plane of the robot. Okay. So it is very difficult to obtain accurate environment modeling. This also requires a force sensor, and it also requires a switching mechanism. When you look closely this kind of controller, so what this end effector interaction is doing, this is basically setting the compliance selection matrix depending on the situation. Okay. So you need a switching mechanism which quickly switches the S matrix elements. Okay. Which direction to choose for position control and which direction to choose for force control. Accordingly, it has some switching mechanisms. There are other issues like tuning issues, stability issues, calibration. You need to have workspaces properly calibrated with the robot spaces, bandwidth of force control. Bandwidth here means the loop. The loop closure should be done at a very high frequency so as to make it very much reliable and very much responsive. Okay. If that control loop frequency becomes slow, the robot responds little slower and it behaves like a stiff robot. Okay. Anyway, as because it has a force sensor which is at the wrist, whole of the robot is almost very stiff. Okay. So these are the limitations with this. Okay. Now moving ahead to a different kind of controller. So far the kind of controller that we have studied had a explicit force sensor and you can command directly for the forces, but there are indirect control strategies also in which force can be controlled, not precisely, but yes, whole of the robot may become little compliance in almost all the directions. Okay. So the one such type is stiffness controller. I am discussing it in a simplified way and reduced it to 3R spatial manipulator here. So it looks like this. Okay. This controller is very simple. Okay. The robot here is driven by the torque. So once it is driven, it gives you an output position trajectory. Okay. This position is sensed here. Okay. Position is sensed here. You extract the position using forward kinematics and current position is fed back to this. So this is the desired position trajectory, this is the actual position trajectory. Difference gives you delta P. So delta P into the stiffness matrix which is here due to the positional error. Positional error into the stiffness matrix generates the force kind of. So this is what is the force. Okay. So force generated out of the error in position is Kp into P desired minus P actual. So this is the positional error that is given by delta P. Delta P into stiffness gives you the force. Force multiplied by Jacobian transpose gives you the torque, corresponding torques due to the positional error. So let us say robot is at its position. If you press it, so it is not at the desired position. So what happens? So whatever is the displacement from the commanded position, so that is an error in position. So it behaves like a spring. So whatever is the compression that you are giving, that generates the force. Okay, it is just like a spring. So end effector behaves like a spring. So this is what is the major control loop over here. Okay, so this is very simple. So force generated is exactly equal to the difference in positional error, that is the commanded and the actual, into the stiffness matrix. Again, this is a diagonal stiffness matrix which gets multiplied with, so its stiffness matrices matrix will look like Kp x, Kp y, Kp z. Okay, it is a diagonal matrix, so any error along delta x, delta y and delta z gets multiplied with the corresponding stiffnesses. Okay, so you can have stiffness different along different orthogonal directions. Okay, so end effector here would behave like a spring. Higher is the compression, higher is the force generated, because after getting multiplied with JV transpose, this is the Jacobian transpose, will give you the torque that actually drives the robot. So corresponding torques are generated. So what are the other torques which is visible in this loop? Let me make it clean. So now tau g is the gravity compensation torque. Okay, what is tau e? Tau is the torque which comes due to the environment interaction. So whatever is the difference in the position here, or you may have a direct force sensor which is here, that can give you the force when multiplied with Jacobian transpose gives you the torque. Okay, so Jacobian transpose into the wrench which is sensed gives you the torque due to the environment interaction. So this is very simple. So this torque is only because of the environment interaction. This torque is because of gravitational compensation. So what is this? Tau v. Tau v is because of the damping which is there in the joints. Okay, so whatever is the end effector velocity, that is known as twist, when multiplied with Jacobian inverse gives you the joint rates. Joint rates into the joint damping matrix gives you the tau v. Okay, so kv into theta dot gives you tau v. This is the damping torque, torque due to the damping at each joint. So now normally all the blocks that are marked in yellow are not there in physical system. In physical system will have natural damping. It will automatically respond to through series of forces. It will come to the joint torques. So you need not to calculate this. You need not to calculate this yellow block here. Okay, a robot will be a physical robot that will be directly driven by the torque, and it will give you the rates, that is at the end effector rate or at the joint rate. So it will directly move. Okay, forward dynamics is not required there. Okay, so this controller is very simple. It makes use of the end effector positional error to calculate the forces. Okay, and finally that is fed to the joint torque and it behaves like a spring. So this is a stiffness controller. Okay, let us move ahead. So these are the equations that I have used here. This is environment interaction model. Tau g is this. Jacobian is calculated like this. The same thing will be used in our controller model once again. Once I will do it in the MATLAB environment here. Okay. So an extended or a generalized stiffness controller that takes care of position error and the orientation error together and feeds you with the torque. So you have tau p due to the position error and tau psi due to the orientation error, and this is the positional stiffness, this is the orientation in stiffness, this is Jv and this is J omega. If you know Jacobian has two components, J omega, Jv, you have already done that. Okay, so those Jacobians will come here. Okay, rest is tau g, environment and the damping terms. Combined together, torque goes to the robot, gives you a position output. Okay, so this is how it works. So you have to extract orientation depending on the type of Euler angle frame representation that is used. You have to convert it to equivalent so that you can multiply with Jacobian. Okay. Similarly, the position extraction is done using forward kinematics and it is fed here. Okay. So, this is a generalized stiffness controller. Now, we will demonstrate stiffness controller using 3R spatial arm using MATLAB Simulink environment. Again, the prerequisite will be MATLAB with a standard Simulink environment, Simscape or multi-body toolbox. Robotic system toolbox will be optional. I will be using embedded MATLAB code for my Jacobian and gravity compensation torque. A paper that I have cited here, simulation of force control algorithms for serial robots by me, can be found IEEE SI 2012, that you can download, you can go through this. So, now let us switch to the MATLAB environment where I will be directly using these equations. So, let us go there. So, this is the environment that I have built. So, you see everything is the same. You already have done Jacobian, you already have done interaction model to generate forces out of the wall interaction, moving plane interaction, can calculate the contact status, reaction forces. Okay. This is the moving obstacle model that you have already done, okay, in the previous lecture. Okay. This is your 3R spatial arm from here till here. So, I am doing whole of the robot modeling here, 3R spatial arm. I am feeding it with the torque which is here, tau 1, tau 2 and tau 3, all 3 are generated from within the stiffness controller now. Okay. And stiffness controller and everything else like Jacobian or gravity compensation, everything is taken from Q1, Q2 and Q3. They all consume this so as to calculate the gravity compensation torque as well as the robot Jacobian. Okay. So, everything is already known. Okay. End effector robot position and the environment position are saved here, that will be used to do interaction modeling. Now, let me get into the stiffness controller. So, what I am doing here is, this is the desired position which I want and actual robot position is sensed here. Okay. Let me just display the controller once again here. If you look closely here, what you will find, this is the desired input which was here. So, desired input comes from here and then actual robot position which was calculated by the robot forward kinematics. So, that comes from here, both of them, and then this is the summing block, it takes the difference. So, this is plus, this is minus, calculates the delta P here. So, delta P goes to the stiffness matrix. So, I have multiplied with the diagonal stiffness matrix. So, stiffness, if I see, it is 500 along x, 500 along y and 500 along z. Okay, that is Newton per meter. Okay. So, this is how I have kept, you can take it anything else. Okay. So, all the models I will be sharing in the resources, you can download, you can try it out. Okay. So, stiffness multiplied by the delta P gives you the force equivalence, and force when multiplied with Jacobian transpose matrix multiply, it gives you the torque corresponding to the positional error. So, this is the tau P which is shown here in the model. Okay. So, this goes here, you can look closely here. Okay. So, that is what is the tau P. Okay. So, here is your position input, this is your robot position, error taking the difference gives you the error, multiplied with stiffness matrix, further multiplied with Jacobian transpose gives you the torque corresponding to the position error. So, that is what is the stiffness that can be realized by the robot, and finally, it goes to the robot using tau 1, tau 2 and tau 3. Other taus are torque due to the gravity, okay, that is calculated here, it goes to the robot through this channel. Okay. Again, you have torque due to the damping, Joint damping, I have taken as 3 Newton meter per angular displacement. So that is here. Okay, so angular displacements are calculated using this Q1 dot, Q2 dot, Q3 dot. Okay, joint rates multiplied by joint damping gives you the joint torque due to the robot joint damping. Okay, so that is what is calculated here. In real robot this won't be there again. Okay, so this is the damping torque input, this is gravitational torque input, this is the environment interaction. Okay, so whatever is the interaction forces which is calculated by our interaction model, that comes through this channel. Okay, interaction model, and multiplied with Jacobian transpose once again gives you the torque due to the environment, that is this one, which is here in this loop. Okay, so this is your all. Okay, all the torques are summed together and sent to the joint. Okay, so this is your stiffness controller. Now let us run this model and see how it behaves. So let me run. So yes, upon running it, it clearly shows the wall interaction. Okay, what is happening here? Let me run once again. So wall started moving, it made a contact, it started pushing the end effector. Okay, wall is moving with 0.05 meter per second towards the robot. Okay, so this is how it behaved. Let me see the plots here once again. So this is your reaction force, how is it behaving? So higher is the displacement, higher is the force which is generated. So if the wall is moving closer and closer to the robot and pressing it, so higher is the displacement from the commanded position. Robot wants to be in its place, so higher is the pressing, higher is the force which is shown, and it behaves in a linear way. Okay, so this is how the force behaves. Okay, alternatively, this time I have moved the wall with 0.05 meter per second. Okay, you can even make the wall stationary and let the robot go ahead and hit the wall. Okay, let me do that here. So if I do that once again, so I'll make it 0. Okay, it moves with displacement is equal to ut, this velocity into time. So velocity becomes equal to 0. Time comes from here, as we did it in the earlier model also. So now I'll use this block which I have kept in comment. I'll uncomment this one, I'll comment out this one here. Okay, so I'll connect this. So what this is doing, this is making the desired robot trajectory input. Okay, so what I am doing, again this is a clock input. It starts from 1.732, the current location of the robot, plus 0.05 into u, that is 0.05 into t. Okay, that is the time. So this is the displacement. Okay, so it is moving towards the wall with a velocity of 0.05 meter per second. Now let me run this. Okay, this again you see the animation here. So it goes, hits the wall and remains there. Okay, let me run it once again. It goes, hits the wall and it remains there, but it will generate more forces as the time progresses. Why? Because you have commanded, you are continuously commanded it to go further and further into the wall. So there is huge difference between the actual position of the robot to the commanded position. So higher is that difference, multiplied with stiffness matrix will create more force. So the force expected here is like this. So it reaches there, it jitters a bit, and then force keeps on increasing. So it behaves in a linear way. Okay, so now you see in a stiffness controller, the problem here is this jittering. It is not a continuous force that you are seeing, because it is a spring like behavior, it is bound to oscillate, right? So oscillation here you can see even while contacting, the contact is established somewhere over here. This is the contact plot. Okay, no contact, no contact, and upon establishing the first contact, it bounces off and it jitters, and finally it establishes a constant contact and it remains in contact. So this bouncing is there. Okay, it doesn't maintain a constant contact, it bounces there for a moment. Okay, and then it continuously maintains a constant contact. Okay, so this is how is the behavior. So this is the problem with stiffness controller, that reaction force is not steady. Okay, so it as expected, so it should be straight line, but it is little bit beyond that, plus or minus beyond that straight line. Okay, so this is the behavior of a stiffness controller. So now let us go back to the slides. So this is what we have seen. So this is a generalized stiffness controller. We have simulated it. So demonstration of stiffness controller, you have seen the problem with stiffness controller. There is too much of jittering upon contact, and the force is not a steady force, and it is not as expected. It should be straight line, or whatever is the compression it is doing, it should generate that much amount of force, but it is oscillating about that point. Okay, so that is not desired. So there is another approach which is known as impedance controller, that we will see in the next lecture. We will see impedance controller and its variants, okay, in the next lecture. So that's all for this lecture. Thanks a lot.